Hello everyone and welcome back. Have you ever wondered if changing the stiffness of the connected plate can completely change how a bolt carries load in ANSYS? In my previous video, I compared beam bolts and solid bolts using two 5mm steel plates. The results were interesting, but they raised an even bigger question. What happens if we make one of the plates much thinner? Will the bolt experience the same forces? Will the beam bolt still represent a solid bolt accurately, or will the difference become much larger? Today we are going to answer all of these questions, so let's get started. If you haven't watched the first video, I will put you the link at the top of the video to the right. You can watch it later on, but for now let's make a quick summary. So, in the previous video we modeled two steel plates connected with M8 bolts, and both plates were 5mm thick, and we compared two different bolt modeling approaches, which is modeling the bolts as a solid 3D geometry, and in the second approach, which is modeling the bolts as a beam elements. So then we compare the bolt forces, stresses and load distribution, and that comparison gives us a good baseline. But in real engineering application, plates are rarely identical in thickness, so that's exactly why today's comparison is much more practical. So for today's simulation, almost everything stays exactly the same. So as you can see on the screen right now, so we have the same bolt size. We still use 4M8 bolt, 8.8. Same material used, we use structural steel, same loading, which is already put it on this face. And we have same boundary conditions and same mesh strategy. So there is only one change actually. Instead of using 5mm top plate, we are replacing it with a 2mm plate. As you can see now, we have on the bottom 5mm plate, and on the top of it just 2mm plate, which is thinner than the one we used in the previous video. So this means the stiffness of that joint has changed significantly while keeping everything else constant. And this allows us to isolate the effect of plate stiffness on bolt loading. So this is actually a very important engineering question. When the connected plate become thinner, they become more flexible. So that flexibility changes how the external load is transferred into the bolt. In other words, the bolt doesn't just depend on the applied load actually. It also depends on the stiffness of the connected members, which is in our case these two plates. So the real question becomes, can a beam bolt still capture this behavior? Or do we need a fully detailed solid bolt model as we have on the right side of the screen? So let's find out. The analysis procedure is exactly the same as in the previous video. I already here solved both of these two models actually. And we will compare the bolt axial forces and shear forces and any differences between both modeling techniques. So because every parameter except the plate thickness is identical, any differences we observe can be directly attributed to that change in stiffness. So before we see the results, as you can see on the screen, I already prepared these two models, which they are already with bolt pretension inside of it. And as we learned before in the previous videos, in order to get the shear forces acting on the bolt, we have to simulate or to initiate the simulation with bolt pretension. And to get the axial forces acting on the bolt, we have to duplicate these analysis and suppress the bolt pretension in order to get the external axial force acting on these bolts. So in these two analyses, you can see that the bolt pretension are on other model, as you can see right now. As you can see here, I already suppressed the bolt pretension, so I can get the axial force acting on the bolts. So first of all, let's go back to the first two analyses with bolt pretension, and from there from the model where we modeled the bolts as a beam, we can get the shear forces, which we can see it from the total shear force. To see that, all what you have to do is to go to solution, insert, and insert total shear force. From this, by clicking on it, as you can see, we can see clearly like how the shear forces is distributed like on the 4 bolt M8 bolt that we have on this model. On the other hand, with the solid modeled bolt, in order to see the shear force acting on the bolt, actually what we have to do is to get from the contact like between the under like head of this bolt and the top surface of the top plate, and from there we can calculate like manually from the reaction forces. As you can see, if I click on one of it, we can see down the tabular data, the reaction forces in X, Y, and Z, and the shear forces by us, it's actually what would happen in X and Z like plane, which is mean like we have to calculate the square root of this value in X direction with the square plus like square plus the reaction forces in Z square, and we can get like from there the shear force acting on this bolt. We will do actually the same thing for each one of these bolts, so we can get the shear force for every one of these bolts. After that, actually, to get the axial force acting on the bolt, I will go back to the left side with the beam modeled, and all what you have to do is actually to click on the axial forces, and from there you can get directly, but not from here, because here we already have the bolt pretension. So we have to go to the model without bolt pretension and click on axial forces, and these actually are the external force acting on each one of these bolts. So I took this and I did put them on the Excel file. We will see it together in a moment. And on the other hand, like we have the model with a bolt as a solid modeled. So from there, without bolt pretension model, from there I go to force reaction on each one of these bolts, and all what I have to do actually to get the force in Y direction, which is described the axial force in these bolts. So this force, and we do the same from each one of these bolts. I did take all these like informations like the axial and shear force acting on these both model approaches and put them in an Excel file. So in this Excel file, as you can see, the first table actually show us the information what we get from the previous video, where we used like two identical plate, which were like 5 millimeter thick, each one of them. And we got actually the following like results. As a conclusion, actually at the end we can see like that modeling like the bolts as a beam will like at the end like give us like it seemingly like identical or nearly like same results as when we model the bolt as a solid. So that means to us like in that case, like as in the previous video, actually the both modeling approach was giving us nearly the same results, so we can use both of them. But in this study, while like we did replace the top plate with a thinner plate, actually we got the following results. So as you can see on the table down, here are for our like actual study now, and as you can see from the first table, here are the informations or reaction forces and axial forces, shear forces for the bolt where they are modeled as a solid. So for this model, from here, like we can see directly that the axial force acting on the bolt were like around like 9,600 until 9,900 Newton, and the shear forces they were like between like 400 or 180 actually at the end of this like for this model. When we like modeled the bolt as a beam, as on the left side, we got actually the following results down, and as you can see the axial forces are like a bit like more than what we get when the bolt modeled as a solid. So we were by 9.9 kilonewton as a maximum. On the other hand, here we are by almost 10.9, which is mean like we have almost 1 kilonewton like more axial force, with the same like model, same boundary conditions, same everything. The difference is actually just we have like a solid modeled bolt and a beam modeled bolt in this case. And if we compare actually at the end from the calculation with bolt pretension, we got the following reaction forces in y direction, which is mean. So here to the right, we have only the external force acting on the bolt, but with the models, when we have bolt pretension already on, we got actually everything together. So the bolt pretension plus the part what the bolt get from this like external axial force together. So I get them these like forces and put them in the y direction. Down you can find them there. And by substituting from these numbers the bolt pretension, which was in our case 18.6 kilonewton, I got the following forces from the first model when we the bolt as a solid model, and these are actually the forces, the difference between these numbers and the bolt pretension when we modeled the bolt as a beam. We can see something like so interesting in this study, which is like actually we got with the model when the bolt model as a solid almost like double this force than what we get like from the bolt when it's modeled as a beam. And that's so interesting because on the previous video we got actually almost identical. As you can see, we were by 9 to 10% and almost the same by the second one, which was like between 8 to 10%. So the only difference between these two studies actually that on the upper side we used identical plate thickness. On the other side, now we use like a thinner top plate, which is 2 millimeter instead. And from that, we became actually this like a huge difference at the end. So this comparison teaches us something much more valuable than simply choosing between beam and solid bolts. It reminds us that the stiffness of the connected structure plays a major role in bolt loading. As you can see, we have here two like it's like in comparison to the previous one and to the one in the previous video, it's our like member are here like less stiff like than the one like in the previous video. So even when the external load remains identical, changing the geometry of the plate changes the internal force distribution. So that's mean two engineers applying the same load to the same bolt can obtain different bolt forces simply because their connected parts has different stiffness. So this is why understanding the entire joint is often more important than focusing on the bolt itself. Now let's summarize both studies side by side. So first study, we had two identical plates, 5 millimeter each. And the study 2, which is we have now here, we have a top plate 2 millimeter thick and bottom plate 5 millimeter. The external loading remained identical and the bolt size remained identical. The only change was the stiffness of the upper plate. Comparing these two cases clearly show how structural stiffness influence bolt loading and how both beam and solid bolt models respond to that change. And as you can see on these results, we have almost double effect, but that was like clearly to see when we modeled the bolt only as a solid, where modeling the bolt as a beam was not like clear to see, which we still have like, we have okay like increasing like on loading on the bolt because before in the previous video we got like maximum at 10%. Now we got like 40%, but it was not like clear as when we model the bolt as a solid, which is like here 35% actually. So this gives us a much broader understanding than looking at only one configuration. So what can we conclude from both videos? First, bolt loads are not determined solely by the applied external force. They are strongly influenced by the stiffness of the connected components. Second, changing the plate thickness changes the deformations pattern, which is in turn changes how the load is shared between the bolt, which is clear to see while modeling the bolt as a solid and not as a beam. And finally, when comparing beam and solid bolt modeling, so it's important to evaluate them under different structural conditions, not just in a single geometry. Only then can we understand the strengths and limitation of each modeling approach. That's exactly why this second study complements the first one. Together, they provide a much more complete picture of bolt modeling in ANSYS. So, as a recommendation from me, if you have like similar like thicker plates and stiffer plates or plate connections, so it's like the same if you model the bolt as a solid or as a beam. So if you have like a lot of bolts, I would recommend then to use like the beam approach, because it's like much like efficient and like no need to do the bolt like as a solid, as in detail, because you will get like nearly the same results. But in case your member plates are like less stiff or like flexible to see it in comparing to the bolt size that you use, so it's recommended actually to model the bolt as a solid and not as a beam, because if you model the bolt as a beam, you will have to expect that the forces that they are coming out, they are not the fully truly like forces acting on these bolts, but you have like actually to model as a solid to get the full like load acting on this bolt. And in our case, it was not like a little, it was a little bit like high, especially for this like a small bolt, which they are like the M8 bolt, which is, as you can see on the table here, where we have the bolt pretension on. As I told you before, the bolt pretension was 18.6 kilonewton. Modeling the bolt as a beam, we got plus the load that we have like maximum at 20.2 kilonewton. But when we model the bolt as a solid, we reach actually around 22.1, which is in some cases could like change our like judgment about the bolt, if they are like okay or not. So, if you found this comparison useful, don't forget to like the video and subscribe for more advanced ANSYS tutorials and structural simulation studies. Also, let me know in the comments what bolt modeling topic would you like me to investigate next. Thanks for watching, and I will see you in the next video.